Mi sembra. Le ho generate non caricate. Qua non c'è. Okay, so welcome to this new class on instruction level parallelism. What we are going to go through today is basically, we try to push as much as possible instruction level. Can you close the door? It's closed, right? Okay. I guess. No, okay. I wasn't sure. Thank you. So basically the idea is, obviously, we try to push as much as possible instruction level parallelism, and we reach a sort of a limit. So what we're going to do today is we're going to work on try to highlight those limits that were not really allowing us to get better performance. We're going to do that by exploiting another technique that we just mentioned, but we haven't seen so far. And then we're going to open the door to the remaining month, more or less, month and a half of this course that is going to be basically change a little bit the way in which we're going to interact with computer architecture and the design of the architecture that we are going to work with. Things are going to be clear in a couple of seconds. So the first thing is, I'd like to remind you that on April 28th, I guess, we're going to have the midterm for the one who were willing to go for the project or the one that were forced to go for the project. That is the high performance processor and system. I'm going to write an email with all the rules because I realized that the thing that I shared were not understood as I was willing to, and you were more scared to try to do it rather than not do it. But there is no penalty unless you're going to do the project. So if you're going to do the project, you cannot do the first appello. If you're just trying to do the midterm and you're going to fail, at that point you can attend the first appello anyhow. If you're going to do the project and you're going to fail the midterm, you're going to have another trial during the first appello. So that is the trade that we are going to make. So that is the thing. That is for the advanced computer architecture class. The high performance processor system, midterm, no first appello, project, and that's it. Whatever they're going to take, they are going to take. So that's their life. But I'm going to write them down so that you're going to have it written down. You can take your decision based on what you think is going to be working for you. I'm not scared to correct more exam. My job is not trying to correct as less exam as possible. It's to teach you. So if you can use the midterm as a way to measure your knowledge with respect to the things that we have done so far, with the intention to go for the project, do it. If at the end of the day you are going to realize that that is what you are not capable of doing, that's it, that's fine. And you're not going to have any penalty. If you're going to do the project, that is a different story. The project is going to be traded with the first appello. Now, with respect to today, we're going to highlight ILP limits, which means that we have to start from the definition of ILP, trying to understand what can be done better to try to push them a little bit further to the points in which we were. And we're going to highlight limits with respect to an ideal case. We're going to see that no matter what, even in working with an ideal architecture, we cannot really achieve the performance that we were hoping to achieve. Which means, on the other hand, that it's not worth it to have an ideal architecture. Because the more you are going to get closer to an ideal architecture, the more you are going to spend in terms of area, in terms of power consumption, energy, and so on and so forth. So that is, again, the point in which we have to decide the trade-off that we are willing to go for in order to be able to, once that we prove that not even the ideal architecture can achieve what we were willing to, how to trade it properly because of specific scenario in which we're going to be. And we're going to have a couple of examples of real architecture. So IRP is quite easy. It's something that you should be already all familiar with. Sorry, I'm going to close the window. It's basically the idea is instruction level parallelism, which means try to overlap as much as possible the execution of instruction. Unrelated. Unrelated means that they are all belonging, obviously, to the program. So it's not that they do not have any relation one with the other. But they are unrelated in the sense that we're not going to have structural hazards. We're not going to have read after write, write after write, and write after read, and no control stores. If one of those is going to come into play, there is no way. The door. Sorry. We do have all our OCD. That's mine. If you're going to have this kind of hazard, there is no way in which we can overlap the execution. And read after write, through data dependency, there is no way in which we can overlap the execution of the two instructions because one instruction is waiting for the data that have to be produced by the previous one. Control hazard, one or the other. Structural hazard, that is in the worst case. I mean, we do not have the resources to not even issue an instruction, so there is no way in which we can overlap the execution. So we have to try to find the biggest number of instructions that are going to respect those constraints. So that is the idea. Trying to push as much as possible instruction level parallelism means to try to find in our code the highest number of instructions that can be executed in parallel. And that is, at the end of the day, the idea behind instruction level parallelism. We are all quite familiar with all those three cases. And if you are going to take one after the other as a single case, it's quite easy. We do have or not a functional unit that can be used to observe a certain instruction. We do have or not a data dependency in between two instructions. We do have or not a write after write and write after read. We do have or not control stores. Now, what if all these things are going to be checked simultaneously at the runtime on all the instructions? So that is the aim. Trying to find the highest number of instructions that can be executed in parallel. It means that that thing has to be done at runtime. It has to be executed by the hardware. And all those things have to be checked simultaneously. On what? The entire set of instructions at every single clock cycle. Because we may have dependency at a certain point. So we want to check what is going to happen next, and so on and so forth. So that means an insane amount of time. That is the kind of trade-off that we're willing to go for. It's great to do that at runtime, but in order to be able really to do that, we're going to take a lot of time just to check all these conditions. So it's something that maybe, great idea, but on the entire set of instruction could not be maybe sustainable in another way. What is going to be interesting is that we're going to observe, I'm spoiling it just because we're not really going to see it, but with execution of benchmarks, which means that you have to trust me in the graph that I'm going to show you, is that even in considering, in an ideal case, all the instruction, at the end of the day, if you think of it, what we are aiming to have all of them to be executed in parallel. That is the objective. Wow. Just one clock cycle, we're going to issue all of them, we're going to decode them, we are going them to be executed in parallel. That is the highest instruction level parallelism. All the instruction executed in parallel. Obviously, to do that, we need to have an ideal architecture that is capable of handling the issue of all the instruction. And how many are going to be? Who knows? It depends on the code, but no problem. It's an ideal case. So we're going to have infinite resources, like the Turing machine in infinite register. That is the thing. The bandwidth, not going to be a problem. We're going to have an infinite bandwidth. What about the latency in controlling the control hazard? Just one clock cycle, no problem. In ideal, we're not going to have any problem. What about the miss? No problem. What about the aliases? Different pointers with this that are going to point to the same address. It's not going to be a problem. Everything is going to be solved. Everything is going to be perfect. Anyhow, we're going to have data dependence, which means that at a certain point, even in an ideal case, we are not going to be allowed to have all the instruction composing our benchmark, our application, our program to be executed in parallel. What is going to be funny is that the number of instructions that at the end of the day could be executed in parallel is not going to be too impressive. It's going to be high, but it's not going to be too impressive, which means that having an infinite issue stage that could issue an infinite number of instructions is not necessary. Having an infinite number of functional units is going to be completely useless because the majority of them, in the majority of the time, most of the time, they're just not going to work. So everything is going to be useless. So that is the thing. The ideal case is, oh wow, awesome. But unfortunately, that thing is not an ideal execution. It's a real execution, which means that we're going to have real applications that are going to be executed on our architecture. And in a real context, those things are there. Read after write, write after write, write after read. Control hazards are going to be there. We can get rid of structural hazards in an ideal case, but it's going to be completely useless. So that is what we're going to see today. We're going to remove the final constraints that we had, and we're going to see that even doing that is not going to be sufficient to try to improve the performance as much as we were willing. That is a sort of this is a transition class somehow with respect to what we did and what is going to happen next. What we did was basically this. We started from sequential, not pipeline code. We were kind of trying to overlap the execution. Pipelining was that idea. And those were the classes in which discussed those things. But then we pushed a little bit further. We were kind of trying to make out-of-order execution because we introduced, obviously there is some in between class 2 and class 7, that was dynamic branch predictor, complex pipelining, and so on and so forth. There were the things that were making the out-of-order execution useful. So that's great, but we realized that anyhow, we are kind of constrained. Constrained by what? The thing that we are going to remove today. Multiple issues. So that is the thing. Up to now, we were working with in-order single issue architecture. What we're going to do today, and that is that the architecture that we are going to introduce today are going to be called superscalar architecture, are going to remove that part. We are going to have multiple issue, out of order execution. In order to be able to find, remember when we were describing Tomasulo? Even with Scoreboard, I guess, at the certain point in one of the figures we had it. But we have the issue window. That was a set of instructions that were the one that were supposed to be executed. The kind of the thing at that point was that we still have a single issue. The one that was on the bottom was the one that was the next to be executed. What we're going to do now is, what if we're going to try to find out in that issue window the instruction that could be executed in parallel. There is no reason to store them. We're just going to let them to proceed. We're going to issue all the ones according to the functional unit that they are going to have that can be issued in parallel. So that is the idea. How big that issue windows is, that was the thing that we were starting from. The ideal case, that issue window is going to be our entire program. We're going to check simultaneously all the instructions. And then we're going to say that even in an ideal case, not really a smart choice. So the idea here is that in order to be able to implement, please.
Isn't it the same with Tomasulo? As long as the data were ready, we were allowing them to pass through the read, but in this case also we are checking the same issue.
Not really, because the issue was in order, and once that you were stalling the issue of the other execution. But now, what we are doing is that we are searching into the issue windows, and we are going to issue simultaneously multiple instructions. We're not going to issue just one. We're going to issue more than one. It's more like very long instruction work, if you want to put it that way. When we were having the compiler to check the instruction and to put them in the very long instruction word based on the functional unit available to be used at that specific clock cycle. What we're going to do now, we're going to do it at runtime. So that is the thing. We're going to solve those conflicts at runtime, and we're going to find the instruction that could be executed in parallel at runtime, instead of having the compiler to do it for us. Better? How to do that? Fetching more instruction. That's the easiest things that we can think of. But it's important, because otherwise we are going to be constrained from a structural results. If you're going to have just one instruction that can be issued, we are going to get back to the original starting scenario. That is not a superscalar architecture. So we're going to be allowed to fetch more than one instruction. The other thing is that we're going to decide on data and control dependency at runtime, which means that superscalar architecture are just an extension of the architecture that we ended up doing on Monday. So we're going to use dynamic branch predictor, we're going to use dynamic scheduling, and all these things are going to be implemented, but allowing us to fetch more than one instruction. So that's it. Quite easy from an ideal point of view. So if we want to go beyond the CPI to equal to 1, and the only example in which we had it was with a very long instruction word, because it was many this scenario. As again, as we said when we were doing very long instruction word, it was more a kind of philosophical question. Is it a multiple issue or a single issue? Again, I'm not going to focus too much on that aspect. Because if you are going to consider the instruction that at the end of the day you are going to issue just one, it's a very long instruction word. But at the end of the day, with respect to the operation that you have, it's a multiple issue, because you are going to have multiple operations that at the end are going to be executed in parallel. And because of this, we were able to have more floating point operation per clock cycle. So that was the reason why we were allowing a CPI beyond 1. That is exactly the same constraint that we have here. CPI 1 over the issue width. How many instructions can we issue in parallel? How many instructions can we fetch in parallel? So that is the level that we're going to achieve. Because if you're going to have 3, it's going to be 1 over 3. If you're going to have 4, it will be 1 over 4, and so on and so forth. Also, that's great. Because if you're going to have an infinite number of instructions that could be issued, it's going to be 1 over infinite. Wow, amazing. That's great. Mm-hmm. You see the second bullet, but it's not really a bullet, but varying the number of instructions per cycle, 1 to 8. What that means, at the end of the day, the number of instructions that we're going to issue in parallel is going to vary between 1 and 8. That is the kind of thing that we're going to have at the end in reality. From an architectural perspective, that is the figure of the superscalar processor. And as you can see, Tomasulo, what we have, reservation station. So that was the first hint on the fact that this was Tomasulo. So we have a reservation station, we have multiple functional unit, comment unit, register file, instruction fetch, and decode. So what is the difference in this figure with respect to the figure that we were already familiar with? Just one thing. Well, 2. Close bracket. Multiple instruction per cycle, multiple instruction per cycle. We are changing also the way in which we are going to get back multiple buses. So the common data bus that we had before has to be extended now. Because otherwise, we are really creating a bottleneck at that point that is going to kill performance. It's going to be quite, I wouldn't say stupid, but really useless at the end of the day. You can fetch an instruction in parallel, you are kind of trying to do the best, and then crunch, you are going to stop all of them and serialize the common data bus. Not really wise. Which means that we are going to have also, at the end of the day, communication infrastructure that is going to be more complicated, more complex. Again, how many functional units? How many instructions are we going to fetch? How many lines for our buses are we going to put in there? It seems the more the better. The more instruction we're going to issue, the highest parallelism we're going to have. The more stages we're going to have in our pipeline, the more overlap we're going to have. Unfortunately, as we know, it's all a matter of trade-off. More stages, complex and more complex control unit to manage the execution of the instruction in those stages. And the same thing is going to happen here. The more we are going to be willing of doing, the more we have to be willing of paying in terms of energy, as an example. So what is limiting the instruction level parallelism at the end of the day? Those 5 things. Well, it's not that those things are limiting, but those are examples of things that are limiting factor with respect to the instruction level parallelism. Register renaming. It's not a limiting factor per se, but we introduced register renaming because we were stalling instruction from, or better, because write after write and write after read. So register renaming is a coping technique to improve instruction level parallelism. We were getting reading of name dependency. They were not through data dependency. We were willing to pay the unified physical register file that we have to introduce. We were willing to use the reservation station in an implicit or in an explicit manner, and so on and so forth. the rationale behind register renaming? To increase instruction level parallelism. Coping with what? The presence of write after write and write after read. That were a problem because of out of order execution. That was a coping technique in order to do what? Increment instruction level parallelism. Always the same rationale. We are looking for the best in terms of performance. We want to push instruction level parallelism to the very limit. So all the things that we did were because of this. And we went to the point in which we cannot do any better, but with multiple issues. That is now the ultimate thing that we can try. Using all the things that we went through. Register renaming, branch prediction. We know that we could encounter in our code branches. So we want to have the best possible prediction technique. Jump prediction. Remember, when it comes to branch, target address, and the outcome of the branch. So the branch prediction is in charge of predicting the outcome. The jump prediction was the address where to jump. Memory addresses, aliases, we didn't go really through a lot of this topic, but it's a problem of conflicting addresses pointed by different aliases. And cycle latencies for all instructions, just one. Remember, what is the latency? Not the execution time. It's the time where we're going to let a new instruction that has to be mapped on the same functional unit to be executed. So one clock cycle, which means for one clock cycle, we're going to have one instruction to use that functional unit, and the very next clock cycle, it's an ideal cycle latencies of one, we're going to have a new one that is going to enter. Perfectly pipelined. That's it, multi-cycle, perfectly pipelined, and at every clock cycle, we're going to have a new instruction to enter into the execution. That is the ideal one cycle latency. In designing something that is going to be ideal, that is the way in which we are going to do it. With respect to register renaming, infinite number. Easy. We saw it also on Monday with the explicit register renaming. We were limited, we were constrained by the number of physical registers. Before issuing an instruction, we had to check if we had a physical register free to host it. Infinite, no problem. Which means that war and war, completely avoided. Because war and wolf are not true data dependency. They're just name dependency. With an infinite set of registers, great, done, solved. Branch predictor, what is the ideal version of a branch predictor? No misprediction. My prediction is always going to be correct. Again, we are not commenting on the fact that this is not possible. We are working in an ideal case. So we are assuming that these things is possible. Jump, as in the previous case, all the jump perfectly predicted. We know exactly where to jump without any delay. All the addresses are known and in a limited number of instructions that could be issued per clock cycle. So that was the thing that we were starting for, having an infinite issue stage. And that is the architecture that we are envisioning, based on Thomas Uno, based on dynamic scheduling, and so on and so forth. So the best that we could have. Now, with these things, I mean, we're just nailing it down again with respect to the specific implementation. Sorry, it wasn't saying the same things a couple of times, but it's exactly the description of the previous slide. What we are going to take, that's quite interesting. Instruction per clock. Integer-based program, floating point program. GCC integer with an ideal situation, we cannot issue more than 54.8, which is not obviously a number. You cannot issue 0.8 instruction, but on the mean, that was the average that we can obtain. Espresso is a place and route tool, a synthesis tool for anyway, we had two, electronic engineering. Espresso, never used. Okay. It's kind of a citation that I'm too old. Tomcat, observer. Okay, thanks. Floating point, 150. Not too bad, but still not as impressive as we could expect. I mean, we can have an infinite issue. That means that no matter how we are going to design our architecture, with an ideal case, everything perfect, no problem at all, we are still limited. The performance that we cannot push further than that. That is kind of providing us a hint in saying, okay, but at that point, if with an infinite situation, with an ideal architecture, we cannot really go beyond certain performance, is there anything that we can try to identify as a trade-off? Well, the thing is, instead of having a infinite number of instructions to be issued, try to limit the window size. Try to limit the window that you are going to use at runtime to identify instructions that can be issued in parallel. Oh, by the way, sorry, there was one optimization that was not mentioned, but that I said when I was kind of spoiling things before the beginning of the class. Everything without overhead. All the control, all the check, everything. Oh, wow, super easy. No problem at all. Even if it's an ideal case. I mean, in an ideal case, I can do whatever I want. I can even start to think that I can work on ads. That is the thing. Everything was just an ideal situation. So the kind of thinking here is that we do want to create a CPU that from an ideal perspective, in a dynamic scheduler, is going to be able to look far ahead without any problem. The other thing is that we want to have the register renaming to be implemented at runtime. So all those things have to be implemented in our architecture because we still do want to take care of write after write and write after read. Determine whether data dependency among instruction, read after write, true data dependency, memory dependency, it provides enough replicate functional unit. So those are the things that we are going to play with in order to be able to design our architecture with limits on our window size. Said that we cannot really push beyond those, we want to try to find something that can be physically implemented that is going to be the right trade-off. And the things that we're going to play with are going to be this. Again, when we do want to check, we want to implement the register renaming, it's going to cost. We saw it on Monday. We do have to check a lot of things. What was the previous register writing that value? We're going to have a new one. We're going to propagate the information. It's going to be physically present or not. There are a lot of things that are going to go behind the scene. So in an ideal case, okay, if we can dream big. But unfortunately, at a certain point, we have to design that thing. And realizing that we are constrained is a great news because it means that no matter what, we have to find trade-off. Even in an ideal case, we cannot really have something that is going to be, wow, astonishing. One of the things is the number of checks that you can make at runtime. Because as we were saying, even supposing that we can do everything, write after write, physical write, everything is going to be fine, work just fine. We are going to be constrained by true data dependency. And the true data dependency is basic. Because I love the formula, but the formula remains a formula, I think we're going to use it. Hey. We're going to have two instructions that are going to be mapped on two functional units. I don't care the functional unit. It could be a multiplication, it could be a division. I don't know. In order to be properly used, we're going to have two input register, the source and an output. Now, what is the, sorry for the name, game, but what is the issue with the issue? In the case in which we were saying, oh, we can physically rename the register. We know that all the addresses have been solved, which means write after read and write after write are done. No problem with conflicts and so on and so forth. Still, we are constrained by what? True data dependency, read after write. Which means that in order to issue those two things in parallel, we have to guarantee that there is no read after write, no true data dependency. Which means that we have to check for this one, this output with respect to this one, and with respect to this one. If one is following the other. Our code is sequential, so we do have already an order. So it doesn't make any sense to check if this one is making a conflict with these two, because in that case, that is going to be, if this is the first instruction in our code, this is our second, it's not really the instruction, it's the functional unit that is going to be used to implement the first instruction in our code. This is the second instruction, this is the second functional unit used to implement the second instruction in our code. What do we have to check? This one is the first. Read of this one after the write of this one. If we do have a read after write, it does make sense to issue them in parallel. Do we have to check the write after write or the write after read? Remember the order? No, because of the physical register renaming. Write after write and write after read are name dependency. Register renaming, solved. So not an issue. Still, read after write are there. Which means that for two instructions, we have to make two check. For three instructions, we have two other registers here and one output register here. Which means that I'm going to check this one with respect to this and this one with respect to this and this one with respect to this and this. What if we're going to have four? We do have to check this one with respect to this and this one with this and this one with the other two registers, this one with those two and the other two, and so on and so forth. The more, the bigger the n, the more we are going to be requested to check at runtime. And that is going to imply overhead, time that we have to spend. So at a certain point, we are going to be constrained by the number of checks that we are going to make. Limiting the Windows issue is limiting that n. Finding the proper n is a great way to implement, to start to think of our architecture. Again, in this case, that is the issue window. It's not the number of instructions that we can issue in parallel. It's different. It's the issue window. It's the number of instructions among which we are going to check if we can find a certain number of instructions that can be issued in parallel. Then we have to have an issue stage capable to sustain those numbers of instructions that are going to be found. Because of this, with a window that is between 32 and 200, we're going to have 2,000, 2,400 comparison to this. Quite big, quite huge, quite impressive. That is the kind of things that we are going to keep into consideration. It'd be great to have that window as big as possible, but the biggest is going to imply higher number in terms of comparison that we have at the end of the day to make, which is going to be, again, the kind of thing that we're going to use and to measure. Instead of having an ideal situation, we are going to have an architecture with 64 arbitrary issues. So that means that this architecture is going to allow us to, in the best case, to implement 64 instructions in parallel. We have to identify those 64 instructions, among which is set of instructions, the window size. So the window size is telling us how many instructions are we going to search to identify the 64 that could be implemented in parallel. What is going to happen is that with the integer program, we're going to have these results. We are going to find at the end that the difference in between the infinite window or the 256 or the 108, 28 or 64 and 32 with GCC is quite limited. So at the end of the day, what this benchmark is telling us is that we do not need to have a window size bigger than 32 because we're going to gain just 2 instructions. Depends on the performance that you are willing to have. 2 instructions, we know that could be a lot. But let's put it that way. 8, 9, with 64, 10. With 128, we're going to match the number of instructions that we can identify with an infinite window. Not bad. So instead of going for an ideal infinite case, we can go for an 128. What about this one? The espresso. Well, here the performance are quite different. 32, we're going to have just 8 instructions that could be issued. We're going to find among those 32, 8 that could be issued in parallel. While if you're going to enlarge the window, we're going to have 15. It's no longer 0.8. Now we know the number of instructions. We have a real architecture that has to use those instructions. So we have to have a finite number. What about the floating point? Again, better the infinite window, 52 with respect to 47, 58 with respect to 45, 17 with respect to 16. Not too impressive. 256 is huge. It's a lot of comparison. No. The infinite is much way bigger. The gain that we're going to have could be not worthy enough, which is an interesting information to decide whether or not to go for a window size of a certain dimension. And we know that the window size is going to have an impact on what? The comparison that we have to make at one time. So those are the kind of things that we're going to play with. When it comes to designing an architecture, it's not all, but it's also about those things. There are a lot of knobs that we can turn, that we can tweak. How to tweak them properly? We need to have an understanding of the domain in which our architecture is going to be used. It's going to be integer dominated instead of floating point. Why not just going for 64? It's going to be floating point. That's it. And it's really going to be like this behavior. All the applications that we are going to execute are going more or less to mimic this behavior. Okay, great. But 17, 15, I can go for 128, which is much way better with respect to 256. It is not really going to pay me back. But because of the comparison that I have to make at runtime, at the end of the day, I can even be worse with the 256 with respect to the 128. All those things are going to be decided once that we have to design our architecture, because once that we have that window size, that is the window size that we're going to use. That is the reason why this class, as the last two that we went through, Tomasulo with the reorder buffer and scoreboard with the explicit register naming, are going to be just theoretical classes. Because unfortunately, we cannot execute those benchmarks. Nowadays, this course is not designed at its best. I'm saying, I'm part of the problem. I need time to redesign this course in order to be able to provide you simulators that could be used to have those benchmarks run on your system. And to see them, because you can see how to play, and you can see that by changing the window size on a simulator, you are going to have different execution time. You are going to have a different results in terms of performance. And it's much way better than just, oh, I'm going to see the graph and I have to trust him. Well, you have to trust the simulator in that case. But still, it's something that you can play with, something that you can tweak, something that you can try to use to explore different solutions. Unfortunately, it's not what we are going to do in this course right now. And it's kind of a pros and cons, because the pros for you is that the cons is that you cannot really experience it. The pros is that if you cannot really experience it, I'm not going to provide you too hard a time during the exam. Because the only thing that I can ask you is the rationale behind things. And why are we not going for an infinite window size in a superscala architecture? Because it's not making sense. Why? Because at the end of the day, benchmarking have proved that the performance that we're going to gain are not going to pay off. That is the thing. In a real implementation, IBM Power 5, dual core, those are, at the end of the day, the numbers of a real architecture. Instruction issued, 4. Not even 64. 4. Instruction window size, 200. In between 126 and 256, with 4 just issued. So that is giving you the sense of the trade-off that we have to play with. In order to be able to fit those 4 properly, we have to play with, in a general purpose architecture, without knowing the specific domain in which it is going to be executed, with a 200 window size. The naming register, 48 integer, 40 floating point. So the physical unified register is of those dimensions. Branch prediction at the end of the day is between 2 and 6%. So those are the real numbers that we are going to obtain by our architecture, which is kind of providing us a situation in which what are the number of functional units? We had an example before. Just 4 issues. So how to tweak all these things? Those are exactly the kind of trade-off that we are going to play with. Again, sorry for repeating. And those are examples of real architecture using this technique. The maximum is 6 in this architecture. So ARM11, Cortex A8, Pentium Pro, well, I told PowerPC, G5, we're having an issue of 6 instructions, which is really quite limited. It's because it was the trade-off that we were willing to play with in order to gain in performance. Because otherwise, we were just losing in performance because there were too many comparisons, a lot of energy that was just consumed by not gaining any performance back. That is the thing. It is not that we cannot do better in terms of performance. But those are the best physical, real implementation with respect to possible trade-off. In gaining that clock cycle in speed may not pay us back in terms of energy consumption. And that is exactly the problem that we are facing nowadays with all these new fancy, great architecture that are so awesome. It's great, but when the hype is going down, and when we do have to make it sustainable, now the things are a little bit more complicated because we're all interested in using ChatGPT, whatever, to design our anime version of our photo. But unfortunately, that means that we're going to have an insane CO2 footprint. And 29 euro, 19 euro per month is not really going to make this entire market sustainable, which means that we need to define better architecture to consume less without losing in performance. Why are we taking now much way longer time to produce our text or because we are slowing down? We do have more services to be served and so on and so forth. So the more people are going to use it, and if you're not willing to pay in terms of energy saving, there is no way in which you can try to make it sustainable. So we need to come up with something different. You are at the perfect time to work on these things, because that is really a need of designing new architecture that are going to consume as less as possible, to even doing really heavy computational tasks like AI, model, and so on and so forth. So the kind of thing here is Superscalar and VLIP. We have these two sort of way of doing things. Superscalar, dynamic scheduling. We're going to use dynamic branch predictor. We're going to use Tomasuno as an example. We're going really to be effective in terms of responsiveness, but in terms of energy, just really killing. What about VLIP? Well, VLIP, where everything has to be computed at design time. We are not using dynamic scheduling. We are using static scheduling. We are not relying on the hardware at runtime, which means that our hardware was simpler in terms of control unit. It could be that it's going to require more in terms of area because we were replicating a lot. We had an issue Windows that was really big because of the bundle of the very long instruction word that we have to issue. But now we're working with Superscalar, which means that we are kind of in the same constraint because we're willing to have multiple issues. So this is no longer a cost with respect to Scala architecture where we had just one issue. So when we were working with the previous architecture with a single issue, it was making this kind of sense to say, is it convenient from another perspective? But now that in order to be able to achieve the best in terms of ILP, the CPI, what are we doing? Multiple issue. Replicating fetch stage, replicating commit stage, replicating buses, which was the same things that we were doing in the VLIP. With the fact that we are taking decision at runtime, dynamic scheduling, all the check for the read after write that we have to do in order to find the instructions that have to be issued are going to happen in the runtime. We're going to pay a lot in terms of power, which means over time, energy consumption. Very long instruction word, the compiler is doing the work. The code that we're going to exec, free dependency code, not a problem. Once that we're going to have it, we're going to execute it. Code explosion in terms of memory that we're going to use in Blade with respect to scoreboard, with respect to superscalar. But those are the differences. So that was the point in which, back in the days, 10 years, 12 years ago, we were kind of using superscalar architecture for, well, now 15 years, I would say. Superscalar architecture for server and Glib for not really embedded system, but DSP as an example, domain-specific solution where we were really looking for performance in terms of energy saving. So those were the two things. Nowadays, things are a little bit more complicated. And as we know, we are mixing even those two things together. I provided you an example of a very long instruction word that is being used into commercial architecture in 2010. That was the Tailea architecture made out of the MIT RAW multi-core solution, which is exactly the kind of things, this is a sum up of all the possible solutions that we can come up with. Now the idea here is, at this point, we tried our best. We designed something that was ideal. We started from instructions that were executed one after the other. Super boring, super annoying, really not performing. Pipelining, great. Pipelining was good, but the deepest the pipeline, the more complex the control unit. Try to find something trade-off again. And then that was a problem with data dependency, and we were not really gaining a lot in terms of performance. Remove those constraints. Out-of-order execution. Out-of-order execution is great, but it's introducing even more hazard, because not only the true data dependency, but also the name dependency that could generate write after write and write after read. Get rid of them. Register renaming. Dynamic scheduling for the out-of-order execution. Complex pipelining, mixing all the things together. Still, one instruction issued at a time. Constraint. Superscalar architecture. Go ideal, go whatever. Still, we are going to pay in terms of energy. Shoot, whatever we're going to try to do is going to bring new trade-off on the table. That's it, end of the story. So we need to try to find something that is going to be disruptive, something that is going really to be new in terms of architecture. And that is exactly, this is just summing up all the limits that we just said and we just went through. Because this figure is showing you a physical issue. We're gaining in terms of transistor, so we're trending up, that's great, but we're kind of limited in terms of power and frequency. So that means that we cannot really push just to put more things into the architecture. It's not going to be convenient. That's it, end of the day, end of the story. We cannot just rely on the electronics guy, on the electrical engineering, and try to have them to squeeze. I think that we did also in this class, the dark silicon phenomenon, where we were shrinking the architecture, but power and energy were not paying back. That is exactly the thing. So we are not following the same trend. And if we can have more, but we are not going to be able to pay less in terms of power, we're just going to put more, and we're going to consume more power. So we just move the roof for our performance. But we're still constrained. Is there anything that we can do at this point? Unfortunately, no. That's physics. That's the limit. Yeah. Unless we're radically changing the technology that we are going to use, that is the thing that we're going to hit. But we are computer architecture there. I'm not an electronic or an electrical engineering guy. I can design novel computer architecture. NVIDIA is not creating its processor. We are creating the design of the processor that are going to be implemented by TSMC. That is going to make the worksheet. If you're interested in knowing more, I'm more than happy to discuss it, because this is really going to be an issue in the following, now I guess months. It was years, but it's really going to be months. But that is the thing. They are just designing the architecture. They are not pushing the technology to implement that architecture. This figure was technology related. It's not design related. So, is there any way in which we can do any better? In this case, the answer is yes. But we have to change the way in which we are going to approach, from a methodological perspective, our architecture. What we did so far was just to try to push and to create a core that was as big, as performant as possible. Try to change it radically. Try to go for different things. That in our class means to really go back to the first class, in which we were already opening the idea to this slide. Because when we started this course, we were saying that we were doing things in a procedural way, in a serial way. But the word out there is not serial. Right? Phenomena are happening in parallel. Even right now, you can hear me, but you can look at me. You can do things in parallel. You cannot just hear or look. And even if you can just do one of the two, you can breathe, because otherwise you're going to die. And you can stand. You are sick, but you can stand. So even ourselves, each of us, is doing things in parallel. So why not doing the same things with architecture? And this is a very, I don't really like this definition, because it's definitely general. A parallel computer is a collection of processing elements that cooperate and communicate to solve a large problem fast. Internet seems to be a parallel computer in that sense. So that's why I don't really like this definition. It is recognized as the first definition of parallel computer. '66, a man in Stanford, Professor Michael Flynn, defined this taxonomy way back to a physical implementation in the days with respect to the physical implementation. When he was calling the MIMD, multiple instruction, multiple data, that he was thinking of parallel processor, but there were none. There were merely microcontroller at that day. So that is the thing. But nowadays it seems, oh, sure. What the hell? It's easy. Yes. Now, in 1966, even of the taxonomy. SMID. What are we going to execute? Instruction and data. Instruction and data. In which way are we going to execute them? Single, multiple. Are we going to have single instruction executed on single data? Are we going to have multiple instructions executed on single data? Are we going to have single instruction executed on multiple data? Are we going to have a multiple instruction executed on multiple data? So that was the amazing thing. It was not starting from, well, he is a computer architecture guy, but it was not starting from the architecture per se, but it was starting from the things that were executed on the architecture, data and instruction. Because at the end of the day, that is what we are doing as computer architecture person. We're just trying to speed as much as possible to make it as efficient as possible the execution of instruction on data. That's it. Which means that our architecture are going to be defined based on the way in which we are going to make those instruction and data executed. Single or multiple. Now, the kind of interesting thing here is, and it's a kind of a historical note that I'm used to present because I think it's important, is you're doing a school in which the person who made the history of the things that you are studying are out there. They are alive. You are not studying a topic that in order to be understood has to be studied only on books. But you can be in a situation in which the things that you are studying are not even yet written in book. Because the things that you are studying are really at the edge of the research that is going on during those days. And things that are now old, taken for granted, were made by people that are still alive. And I'm speaking of the man on the right, but also the man on the left, as far as I know, as far as it seems. But he is there. You can go to Stanford, but do not just knock at his door and pretend to an appointment with him. But those are the things that you can do. You can meet with people who made the history of the things that you're studying. You can work with those persons. You can be really part of this story. So that was the message. Do not consider yourself as someone who's not going to make it, because you're going to be the weight on your potential. And that is sad. You can really be someone who's going to change the things, because you are in the proper school, challenging yourself in a context in which nowadays the history of the things that you're studying is happening. And the distance in between you and who is making the history is really fine. So I hope that at a certain point someone is going to be part of that story. Since the architecture, those slides, I don't recall if I showed during the first slide, the first class or not. It was just 5 minutes and we are done. So just a kind of short go through the things that we may have already seen. Single instruction, single data, standard way of doing things. 5-stage pipeline mix. That's it. If you have to think of an example of a CSD, 5-stage pipeline mix. The architecture that we went through from class 2 to class 6. That's it. That is the code that we're going to execute. Is obviously is going to be translated. We went through it and it was really super boring, so we're not going to do it again. But we're going to translate that code into something that can be executed on the architecture based on the architecture that we are going to use and is going to be implemented. That's it. SIMD, single instruction, multiple data. Vectors. That's it. GPUs are an example of architecture that are implementing a SIMD way of doing things. The kind of interesting thing here, and that is the remaining of this course, is that we're going to see that this is a taxonomy. SIMD could be an architecture, or it can even be part of an architecture. We may have, do you remember what was the instructions? The ISA, instruction set architecture. The physical implementation in our architecture of functional unit can be used, that can be used at runtime to implement operation to map on those functional units. One functional unit could be a vector unit. We may have specific instructions that are going to be vector implementation of, I don't know, 10 points, 5 points, 8 points, who knows how many points, I mean, data that we're going to use in our vectors. So that is the thing. We can have integer operation or we can have vector operation in a single instruction set. Think in MATLAB. For MATLAB, everything is a vector, but we can have scalar or we can really have vector. What if we are going to have physical implementation, a physical one-to-one mapping with the instruction scalar, vector? Could be super fast. So that is the thing. Those are ways in which we can implement accelerator. Hardware accelerator are not just FPGA, are not. Back in the days, there were multiplier, MMX. Those were extension for making certain computation to happen. They were not just part of the architecture, they were accelerator. We can see SIMD instruction as way to update our architecture. Or we can design SIMD architecture, GPUs, graphical processing unit, not GPUs, GPU. MISD, multiple instruction, single data. That seems to be weird. Multiple instruction on a single data. Why do I have to do multiple things on a single data? Because I may want to check something. Packet inspection, pattern matching, regular expression at the end of the day. The data is going to remain the same, and we're going to match with multiple expressions. So multiple instructions on a single chunk of data. So those are kind of an example of architecture that are now implemented this part of the taxonomy. And then the final one, MIMD, multiple instruction, multiple data, which means that we're going to have several parallel instructions that are going to be executed simultaneously on data that are going to be different one from the other. Again, this is a taxonomy. It's not a physical implementation. One way of seeing it is a superscalar architecture could be an example of a MIMD. Multiple instruction, multiple data. Multiple issue, we're going to have multiple instruction executing their operation on multiple data. So it's a way to implement it. Or multicore. Take a MIPS architecture that is a single instruction, single data, and make a replica of it into a single chip and create a multi-core architecture with 8 MIPS architecture that are going to execute 8 threads in parallel. In that case, the architecture is going to be a multi-core that is going to execute multiple instructions on multiple data. The single core is a SIMD architecture. And that is why I was saying now things are going to be interesting. Because we're going to combine all these things together. We can even play with heterogeneous computing. We can have multiple instruction, multiple MIMD architecture, better multi-core architecture that are going to be heterogeneous. We can have specific DSP core for AI, for DSP core for music delivering, for graphical purposes, or we may want to have specific core to make computation for AI and all the physics and so on and so forth. And we have to orchestrate them all together, which means that we need to provide those core data and so on and so forth. So now the things is really going to get more exciting because it's no longer just one core, but it could be go beyond the single core and try to design something that is still going to perform well in a context in which it may have to interact with others that maybe are going to be even different from itself. That is exactly the kind of things that we are going to start from the next class. We're going to start to see GPUs, and that is when the projects are going to come into play with respect to me in this class, not for the high-performance processing system, but just for the advanced computer architectures class. We're going to have an introductory class on GPUs. Then we're going to have a week in which we're going to dig into more details on CUDA, memory model, and so on and so forth, to see how to use GPUs efficiently. The things that is going to be true for everyone with respect to the exam is the theory. I'm going to ask you things with respect to the memory hierarchy in GPUs. I'm going to ask you things with respect to the way in GPUs are built and the way in which they are working. I'm not going to ask you things about CUDA. Why are we doing this? Because it's going to be a crash course of 2 lessons on how to use GPUs in order to be able to, the week after, we're going to have a class on graph machine learning. We're going to provide you a specific domain in which those architectures are useful. We're going to describe you why, based on the things that you learn, those architectures are the one matching at the best the graph machine learning domain. And we are going to provide you 2 tracks that you can use to make the project. That is going to end at the end of June. So those are the timing and the organization with respect to the class. After GPUs, multi-core, cache coherency, cache consistency, 1 class on FPGAs, and then we're going to be done because it's going to be the end of May. Thank you all. I hope you survive the class and see you, well, happy Easter. No matter if you're going to celebrate it or not, you're going to be in vacation, so it's going to be anyhow something to celebrate. See you next week. We're going to have the TA online on Wednesday. Monday, we're not going to have any class. It's going to be vacation. Wednesday is going to be online. Then you're going to have another bridge because of May 1st. But in between, you're going to have the midterm for the ones that are going to attend and try the project, or they have to. Thank you all, and see you next classes that I don't know when is going to be.